Okay, good morning, everyone. Today is lecture one of the AER 1217 course. My name is Dr. Longhao Chen. I'm going to give this lecture for you today. So this lecture is about the quadrotor dynamics and control. So this course is a second part of the CARRE core courses, following AER 1216. So the focus of this course is placed on development of unmanned aerial systems with a theme autonomy in navigation and control, as well as flight performance analysis and evaluation. So in today's lecture, I will going to cover three main topics. So the first one is quadrotor dynamics. The second is some kind of control methodology that are widely used in autonomy in terms of quadrotors. And the third part is how to apply those control methodology in actual UAS. So this is outline of the course. The motivation of this course is that in order to use this highly maneuverable and also mechanically simple system, such as the quadrotor octorotor, we need to understand the dynamics and design the corresponding controller, such that it can fly safely and according to our planned mission. So for those kind of platforms, it is inherently unstable, meaning that if there's no feedback control, then it will not perform the desired mission, and also it will deviate from the path without returning. So traditionally, if we want to control such systems, we usually rely on manual control, where a pilot use his eyes and the radios to control the drone. But the goal of this course is to enable you to design an automatic system such that we can use computers to perform automatic control on such unstable platform. So why dynamics control? Because quadrotor is inherently unstable. So meaning that if there is a tiny push from the equilibrium, and the quadrotor will just fly away from the equilibrium without returning. And in this case, we need to study the feedback control and how to actually apply those controls on such platforms. So the first section of this lecture is about the dynamics. So before I introduce you the full dynamics equation, here are some background of related mathematical backgrounds. So for a vector used in this lecture, I use a symbol with a arrow on top of it. I think everyone should know that there is an inner product between two vectors, and there's a cross product between two vectors. In order to describe and do algebra on vector algebra, vector and their products, such as inner product and cross product, we need to define their coordinates in some coordinate frames. So for example, a coordinate frame is formed by in three-dimensional space is formed by three unit vectors called a basis vector. So A1, A2, and A3. So these three vectors are perpendicular to each other and has a length of 1. So the coordinate of a vector expressed in some frame, say frame 1, is defined by using the inner product. So it's the coordinate on each axis is actually the inner product between this vector and the basis vector. So for example, if we have a vector B, then the coordinate of the B in the A1 axis is the inner product between these two. And also it applies to all three dimensions. So since we have definition of the coordinates, then the key idea is that how do we express those vector calculations, such as inner product and the cross product, in terms of a coordinate form. So for a cross product in this format, so for example, if we have a vector C that is a cross product between A and B, we're going to use this so-called skew symmetric matrix formed by A1. So for example, right now suppose that we have a coordinate system called frame 1, And the B1 is the vector B, the coordinate of vector B expressed in frame 1. And this A1 hat is a 3 by 3 matrix, skew symmetrical matrix, formed by the coordinates of A in frame 1. So then the coordinates of C expressed in frame 1 is actually the matrix product between A1 hat and the B1. So where A1 is a skew symmetrical matrix expressed in this format. So with the help of coordinates, we can actually convert the vector algebra into a matrix algebra. And of course, by using the property of the cross product, we know that if we do the transpose, meaning that if we swap the order of the cross product, it will give us a negative result. So same here. So if we do the transpose of this matrix, it will give us a negative because it's skew symmetric. And also it has a relation of being linear. So basically, if the vector forming this skew symmetric matrix is a summation of two coordinates, then the result can be expressed as applied in this skew symmetric matrix map, but adding these two results together. So for inner product, it's easy. So it's just if we have an inner product between A and B, vector A and B, the inner product in terms of coordinates is just one A transpose times B1. So the final property is a little bit complicated, but it's going to be used throughout the derivation of the dynamics. It's called the vector triple product. Basically, we do the cross product between B and C first, and then use this result to do another cross product between A and the result of B cross C. So this there's identity of this triple product. It equals to the inner product between A and C times B, and the inner product between A and B times C. So again, we can express this inner product, triple product in terms of coordinate form in the following way. So if we have a skew symmetrical matrix formed by A and B, so if we do this matrix multiplication, it equals to the following. So we have here we have two matrices that are all skew symmetric. So it equals to a vector, so column vector times a row vector minus a scalar times a identity matrix. So this is a property of this skew symmetric matrix from the vector triple product. Okay, so and then so there are two coordinate frames that are widely used in the control and the dynamics of quadrotors. One is called the ENU frame. So it's E means east, north, and up, and one is the NED frame. So it's short for north, east, down frame. So you often see these two frames used in the application of control in terms of quadrotors and multirotors. So one of the key aspects of controlling the quadrotor is to control its attitude. So how to express its attitude in terms of mathematical quantity is very important. So there are several ways that we can use to describe the attitude. So the most commonly used one is called Euler angles. So basically we have some rotations angles around some principal axis. For example, if we rotate around the z-axis, it's called a psi. So it's like a yaw angle. If we rotate around, say, the x-axis, it's called the rho, and for the y-axis, it's called the pitch. So by using the rotation angles, we can form some rotation matrices between these two axis frames. For example, this is frame 1 and frame 2. Then the rotation matrix between the two reference frames by the principal rotations are given as follows. So you will often see those matrices used in the kinematics and dynamics of quadrotors. So the other way is that because if you use Euler angles, you are going to run into the issue called gimbal lock. So which means that there's a singularity when the pitch angle reaches 90 degrees. So in order to avoid that problem, especially for controlling the drone with very large and agile motions, we need to use some alternative ways. So a very important way to do that is just to directly use rotation matrices to describe the attitude. So for example, if we have two frames, say frame 1 and 2, and if we have a same vector, x, and in the frame 1, its coordinate is x1, and in the frame 2, its coordinate is called x2. Then the rotation matrix R12 is the transformation between these two coordinates. Okay. And of course, for rotation matrix, the inverse is transpose. And here we also use the notation. We also use notation that if we want to express a transpose or the inverse, we just swap the indices. So for example, you will see here we have R12, and we have x2 here. So meaning that the vector with the indices should be the same as the second indices of the rotation matrix. So we have this vicinity rule. And so if we have another coordinate frame, so here, for example, say the frame one is denoted by using A1, A2, and A3. So these three basis vectors form frame 1. And E1, E2, and E3 form a second coordinate system. So they are also three perpendicular unit vectors, but has some rotation angles. So then we can. So if we know that the basis vector forming the frame 2 expressed in frame 1, if we know the coordinate, then we can directly form the rotation matrix by just stacking all the coordinates in the direction of row together, and we're going to have R12. So any questions? So if you have the basis vector forming a coordinate system, you can easily construct. Yeah, so that's a good question. So in later control, the control goal is to set the desired lift direction. And the desired lift direction is usually given by extracting the direction of the desired lift as a unit vector. So in this case, you have a unit vector rather than a series of Euler angles. But you can still do that. But if we have this relationship here, we can directly use the direction of the desired lift together with some other constraints by the heading angles to construct the desired attitude more conveniently. So this relationship is just to eliminate some Euler conversions, such that you can directly form in the attitude by trajectory error. Yes, because this matrix is formed by unit vectors in different coordinate frames, right? So as long as you can provide the direction of basis vector, I can form the rotation matrix. But if you use Euler angles and you are the pitch angle is 90 degrees, then you will have to then the yaw angle and the roll angle are the same. So you have to, if you have infinite number of solutions you can pick for determining whether how much is your roll angle and how much is your yaw angle. So that is the point where you have issues, numerical issues in terms of controlling. Good. Okay. So if since we have the rotation matrix between two frames, then we can express the inner product between two different reference frames. So this is the inner product we used in frame 1. So right now we have a vector A1 and vector B1, vector A and vector B. So the inner product between these two expressed in frame 1 is A1 transpose times B1. Now, we apply the rule of rotation matrix, and then we can directly replace A1 with R12 times A2. And we can replace B1 with R12 times B2. So this is actually B1, this is A1. By using the definition of the rotation matrix. And then we can say that, we can immediately know that since we have a transpose here, the rotation matrix ahead of A2 goes to the second place. And then we also know that the transpose of the rotation matrix is inverse. So it results in this form that these two rotation matrices cancel each other. So we can see that the inner product will remain the same because it's a scalar in any reference frames. Right? And for the cross product, if we want to describe the cross product into different coordinate frames, we can do the same. So if we use if we say we describe the cross product in frame 2 as A2 hat times B2, and because this is the same result, say C, but expressed in frame 2, so we can actually use a rotation matrix to say that, okay, so since we have some C1 that is expressed in frame 1, and the transformation between C1 and C2 is R21. And here, because the C1, now C1 is equal to A1 hat and B hat. If we replace B2 with R21, then we can say these two relationship are these two expressions are the same. So these two are the same, but it should also be valid for any B1. Meaning that A21 A hat is equal to A2 hat R21 for any B1. Because if it's valid for any B1, we can replace B1 as a series of unit vectors. So since this relationship should be valid for any B1, and these two are the same because what's inside here is C1, but the same cross product expressed in frame 1. So R21 times A1 hat B1 equals to R2 hat times A21 B1. Because it's valid for any B1, so we can replace B1 as a series of unit vectors. For example, this is 1, 0, 0, is 0, 1, 0, and this one is 1, 1, 0. So this, by picking this very particular combination, this equation will actually be converted to R21 times A1 times E. This is identity matrix equals to R21 times B1 times E. So the E is actually composed of E1, E2, and E3 here. So because this one is an unended matrix, it means that the above equation is equal to R to 1, A hat 1, and A2 hat times R to 1. And then finally, if we move the rotation matrix, or if we times the rotation matrix, if we time the R1, 2 on each side, will resolve in the final form. So the thing is that if we have the coordinate of, we have a coordinate of a same vector A expressed in frame 1 and frame 2, then the skew symmetric matrix generated by these two coordinates has the following relationship. Yeah, so we're going to use this to do the cross product, but in different frames later. Okay, so that's so much for the algebra in different coordinate frames. So now the very important topic here is the angular velocity, the definition of angular velocity and how it's going to be applied in kinematics and dynamics. So the angular velocity is defined as the rotation rate of a unit vector. Say, for example, if E is a unit vector here, and then we perform an infinitesimal rotation by the rotation angle of delta theta. And then we use the omega to describe a plane where this infinitesimal rotation happens. So we'll say that, okay, the E, the unit vector E is in the plane defined by the normal vector of omega. And also the delta E generated by this very small rotation is also within the plane defined by the omega. So because the rotation angle is very small, and also the length of E is 1, then we can approximately say that the length of the increment of E is approximately delta theta. Right, because it's like the radius times the arc angle. So now we get the magnitude of this very small increment by using the rotation angle. So if we also say that this normal vector omega has the magnitude of theta dot, so which is a rate of change of the theta. Then we can also the magnitude of the increment is the magnitude of omega times delta t. So that's how we get the magnitude of the angular velocity. Now, what about the direction of this small increment? So take a look at this picture here. The small increment is in this direction, but it is within the plane defined by this normal vector omega. And also, because it's a very small infinitesimal rotation, it is also perpendicular to E. Now we can immediately see that this satisfies the definition of cross product. So if we do the cross between omega and E by using the right-hand rule, it will actually give us the direction of delta E. And because we define the magnitude of omega such that it is equal to the rate of change of theta, then the magnitude of this cross product will also satisfy this condition. So here, by doing this cross product, it will also give you a delta E with the magnitude of omega times delta t. So by doing this analysis, we can immediately see that, okay, if we have our angular velocity, omega, and we have a unit vector that rotates around this omega, then the infinitesimal increment of this unit vector is the cross product between these two. And of course, times the infinitesimal time period. Then, if we move the delta t, so the delta t is original here, and we move it to the denominator of the left-hand side, and then we take the limit of the delta t. This is the definition of the time derivative of delta e of e, right? So it tells us if we know omega, and by doing the cross product, we know that the time derivative, the rate of change of this unit vector is a cross product between itself and the angular velocity. And also, since we have a definition of coordinate frames, we can express this time derivative in terms of coordinate form. So basically, if we do E1 here, if we use a E1 dot here, this is a skew symmetrical matrix. It's 0, 0, and some other terms, off diagonal terms, times the E1, the E expressed in frame 1. So the reason why we do this is that it allows us to use the chain rule of calculus for subsequent analysis of the angular accelerations and also the dynamics of the rigid body. And so right now we say that the omega is perpendicular to E in this expression. But what if the unit vector rotates around the omega that is not perpendicular? For example, we have this scenario where the omega is in this direction and the E is in this direction. So clearly now we have it's like we define an axis and we have a vector that rotates around this axis. Right? It's like a cone, forming a cone shape. And so if we imagine that there is a plane that is perpendicular to the omega, and this is the E, and this is the E that is perpendicular to the omega. So we can clearly see that if we only analyze the component of E that is perpendicular to the omega, then it goes to the original geometry we analyzed before in our previous slides. So basically, only this E that is perpendicular to omega will create a small increment to the unit vector. So if the omega is not perpendicular to E, we only need to separate the E into two components. One is the parallel component that is parallel to the omega. One is perpendicular component that is perpendicular to the omega. And by the property of the cross product, if we do cross product between two parallel vectors, it's 0. So it actually gives us this. So then the rate of change of E is actually the omega, the cross product between the omega and the component that is perpendicular to omega. From this analysis, we can just safely write the rate of change of E as the cross product between the omega and the E without assuming whether this omega is perpendicular or not, because the parallel component will be cancelled naturally. The reason why we do the analysis of angular velocity and the relation between the angular velocity and the rate of change of the unit vector is that by using this definition, and if we define an angular velocity of a coordinate frame, say right now we have a frame that is rotating relative to frame 1, then what is the rate of change of the rotation matrix here? So here we just directly apply the time derivative to the rotation matrix. Then we will immediately see that, okay, so it is equivalent to say that we need the rate of time derivative of all the coordinates of its unit vectors expressed in frame 1. And by using this coordinate form of the time derivative, the relationship between the angular velocity and the unit vector, we can see that this E11 dot is actually equal to omega 1 hat times E11. And the E21 dot equals omega 1 hat times E21. And E31 dot equals omega 1 hat times E31. So by pulling out omega 1 from the from within the matrix, we can get the following result. So it basically shows that the time derivative of a rotation matrix is equal to its angular velocity expressed in the frame 1 times itself. Previously, we know that, okay, so for a single symmetrical matrix, we can express this hat map, this single symmetrical map, into different coordinate frames. Now we're going just to apply this relationship to omega. So previously, we have this relationship directly from doing the time derivative calculation. And now we know that, okay, so omega 1 hat is actually equal to R12 omega 2 hat R21 because of this relationship. And by applying this, we'll get this component. And we will know that this the third term and the fourth term will cancel because these are inverse rotation matrices. So finally we'll get this result. So the time derivative of R12 is actually equal to itself times the angular velocity expressed in the rotating frame. So why are we going to do this? Because the omega 2 is actually the angular velocity that is measured by the MU. So in this case, if you have omega 2 from your MU, you can directly construct the rate of change of your attitude. So since we have the relationship between the in the kinematics in terms of the time derivative of the rotation matrices, then we're going just to apply this into finding the rigid body dynamic equation of a quadrotor. So right now, although for a quadrotor we have rotating blades, but we assume that those blades are, the mass of those blades are small, so we're just going to ignore its moment of inertia. So we just treat the entire body of the quadrotor as a single rigid body. And we're just going to analyze how this thing will move subject to a force and a moment. So for a system of mass points, so for say a rigid body such as a block, we can separate it into an infinite amount of very small components. Right? It's like a system for point masses. However, because we have a rigid body assumption, then we'll see that, okay, so if we describe a single point mass within the rigid body, the position of this point mass with respect to some reference, some body fixed frame as P, as vector P. So for example, if we define a body fixed frame on the rigid body, and then for a very small point mass here, the relative position from this point mass to the center of this body fixed frame is P, the vector P. So if we say we express the vector P or vector Pi for the ith point mass in frame 2, which is the body fixed frame, as Pi2. So Pi2 is the coordinate of the vector P expressed in the body fixed frame. So by applying the rigid body assumption, because we say this is a rigid body, so point mass should not move relative to the body fixed frame, right? Then we say that the time derivative of pi2 is 0 because of the rigid body assumption. And of course, all the point mass, if we sum all the point mass together, it should equal to the total mass of this rigid body. And in terms of picking the body fixed frame, here we do not just randomly pick one. We're going to pick one that is a very special one with its origin at the center of mass. So by applying this condition, we say that the weighted sum of all the coordinates of pi is 0, because the center of this body fixed frame we pick is at the center of mass. So the definition of center of mass is that if we have weighted sum, it should be weighted sum according to the single point mass. It should be it should equal to 0. And no matter where you express this summation, it should always be 0, because the center of mass is it does not change, right? We express in several different reference frames. So by applying the rigid body assumption and also the center of mass condition on the body fixed frame, together with Newton's second law for a system of point masses, we can obtain the rigid body dynamics of a rigid body dynamics for like a piece of block. So the first step here is that for a single point mass, say delta m I, the position of this very small infinitesimal mass is the xi, expressed in frame. Say we express in frame 1 is like the r1 plus the pi1. So the r is the displacement of the body fixed frame from the inertial frame. It can also be expressed as r1 plus rotation matrix r12 times pi2. Right, because by using the rotation matrix, we can express expressed with the relative position of the point mass expressed in the body fixed frame. Okay. And remember that since we use the rigid body condition, the time derivative of the position of a point mass in the body fixed frame does not change because it is a rigid body. Now, in order to obtain the inertial velocity of this point mass, what we do is just use to apply the time derivative on both sides of the equations. So if we apply the time derivative on the left-hand side, so x dot I1 is just vi1. So it's the inertial velocity of this point mass expressed in frame 1. So where frame 1 is the inertial frame. And for the right-hand side, we're going to use the relationship between the angular velocity and the rotation matrix. So R1 is just R1 dot, right, the same. But here, R12 times Pi2, if we use the time derivative on this matrix multiplication, it will give us, then we apply the chain rule, right? So it should give us 2 terms. So if we take the time derivative of this term, it will give us R12 dot times Pi2 plus R12 times Pi2 dot. And because this is a rigid body, we know that Pi2 dot is equal to 0. So for this time derivative, we only have one term left, which is the R12 dot times Pi2. And we're going to replace the R12 dot. Oh, sorry. So we're going to replace R12 dot with R12 times omega 2 hat, because there's a relationship between the angular velocity and the rotation matrix. Okay. So the final form is this. So the inertial velocity of this point mass is equal to the inertial velocity of the body fixed frame plus a velocity induced by the angular velocity of the body fixed frame. Good? Okay. Then what about acceleration? So in order to apply Newton's second law, we need an acceleration. So what we do here is just, okay, so we take the time derivative of velocity again, and it should give us the inertial velocity where we can apply Newton's second law. So here, for the left hand side is just v dot I1, and the right hand side here is this v1 give us v1 dot. So this is the inertial acceleration of the body fixed frame, and then we need to take the time derivative of this entire thing. So it will give us actually three terms. So by applying the chain rule, right? So because we have a multiplication over two matrices and then one vector, so it's equal to applying the time derivative on the first one, and plus applying time derivative on the second one, and plus applying the time derivative on the third one. And because we have the rigid body assumption here, the third term is 0. Okay, so the only the term left is the first one and the second, the first term and the second term, so which is the result shown here. If we apply the time derivative of the rotation matrix again, we can replace the R21 dot by using R12 omega 2 hat times omega 2 hat times pi2. And for the third term, because we know that A cross product B is equal to minus B cross product A. So we can actually swap these two terms and add a negative sign here. So it's like a with, so previously we have omega 2 dot cross product of omega 2 dot between and the pi2. Now we do the cross product of pi2 and omega 2 dot. Because we swap the order of the cross product, we need to add a negative sign here. Okay, so that's the acceleration of a point mass on a rigid body. And since we have acceleration, we can apply the Newton's second law. So in the translational channel, we have the following. What we do here is that we directly do a weighted sum of all the inertial velocity of each point mass. And it should give us the total force on the entire body. So previously, what we have here is that, so the Newton's second law tells us that, okay, so if we do this, if we sum all the acceleration weighted by the infinitesimal mass, it should equal to the entire, which equal to a summation of all the external forces on the body. So then we do that. So because if we do the summation, okay, and then we also apply the assumption of the center of mass. So then what do we have? So delta mi times vi1 dot is actually equal to delta mi times v1 dot plus delta mi times the entire thing. So we apply this Newton's second law, And by replacing the initial velocity of each point mass with the term we just obtained from the kinematic analysis, so we have the following. So delta mi times the the vi1 dot is equal to delta mi times the initial acceleration of the entire entire rigid body plus some residual terms. But then you will notice that these two terms are all the same, and it's only a summation of some product matrices times delta mi times pi2. And because we say that the body fixed frame is located at the center of mass, we have this relation of summation. So if we sum all the point mass together, then the residual terms should cancel out each other, resulting in a very simple form expressed here. It's just the initial velocity times the total mass equals to external force. Right now, it's just Newton's second law applied on the rigid body. Then what about rotation motion? So if we say we time the so beforehand we just directly apply or we just directly use the delta m times the pi and add them together. And then what about rotational motion? So for rotational motion, instead of analyzing the motion as a result of external forces, we need to analyze the motion as a result of all the external moments. So in this case, we see that okay, by applying so if we time the pi, but the sequence metric is formed by pi1, so pi hat on both sides of the equation, and by stating that the body fixed frame is at the center of mass, we get the following. So the vi dot 1 times the mi times the pi1 hat is 0 because of the center of mass of assumption. This is the actual weighted sum of the v1, and if we apply the center of mass, all the vector times the mass should cancel each other. So the only term that is non-zero is what's left. It's like R12 times the summation of the delta mi, and also the summation delta mi times the pi2 hat times omega2 hat times omega2 hat times pi2 minus is pi2 hat and the pi2 hat, the double multiplication of the symmetrical matrix times the angular acceleration. So because this one is 0, what's left on the right-hand side should equal to the total external forces. Okay. So we were going to have the result in this format because the first term cancels each other. So the total, okay, so now the thing is that how do we simplify this term such that it has a relationship to the moment of inertia of a rigid body. So based on some previous knowledge of mechanics, we know that the moment of inertia J is actually the summation of delta mi, these two times the pi2 hat times pi2 hat is actually the distance, square distance times the mass. So this is a definition of moment of inertia. And then we immediately know that, okay, this second term together with this delta mi is actually the moment of inertia. And then, so this one is the actually J times omega 2 dot. And so the final thing is that we have something left here. So then how do we relate this one to the moment of inertia rather than using the vector of single point masses? So here, what we do is that we use the triple cross product rule. So I introduced at the beginning. So for two skew symmetrical matrix times together, if A hat and so the product of A hat and B hat equals to B times A transpose minus A transpose times B times a identity matrix. So here, what we do is that for these two matrices times together we can replace the matrix multiplication with this result. So remember, we have this relationship based on the triple vector product. And we also know that the moment of inertia is in this format. So this term is just J times omega 2. And then the first term here, if we apply this one into the first term, we can expand the second and the third term in this format. So omega 2 hat times omega 2 hat equals omega 2 times omega 2 transpose minus omega 2 transpose times omega 2 times a identity matrix. And one thing is very important, that is the pi2 hat times pi2 is 0. Because the hat is the skew symmetrical matrix formed by the cross product. And for the second term here, is actually equal to, because the omega 2 transpose times omega 2 is a scalar. So that we can pull the scalar out from the matrix multiplication and put it at the very beginning. So this results in the inner product times pi2 hat times pi2. And because we have an identity matrix, so it just vanish here. So the second term here, if we use the property of the cross product, it actually equal to 0. So only the first term remains. Now, what we do here is that, okay, since we only have the first term remains, we swap the order of the cross product again. So again, because from the property of the cross product, this second term is equal to 0. And for the first term, so this term is actually equal to pi2 hat times omega 2 transpose times pi2. Now what we do here is that, okay, this one is the inner product. This one is a cross product. And for inner product, we can just swap. And for the cross product, if we swap, we need to add a negative sign. So okay, now what we do here is that we swap the inner product, so that the pi2 transpose times omega 2 is the omega 2 transpose times pi2 is the pi2 transpose times omega 2. But for the cross product here, we swap. So it's now it equals to the omega 2 hat times pi2, but with a negative sign here. So right now we have pi2 times pi2 transpose. Then we can apply the triple product rule again. So because we want to express the first term also in terms of moment of inertia and angular velocity, right? So you can see here, these two terms are same. So basically what we do is that we swap. So we put something, oh, this should be a positive sign. So it equals to this one plus this one, right? So here equals to because omega 2 hat times omega 2 is 0 by the property of the cross product, then we can add this term because this term is a scalar times omega 2 hat and omega 2. So this term is actually 0, but we can just leave it here such that this subtraction becomes the same as the one in the triple product. So this one is 0, and this is the first term pi2 times pi2 transpose is the same in the previous expression. So if we have this relationship, we can replace the entire subtraction here with the multiplication of two scale symmetric matrix. So this actually gave us the pi2 hat times pi2 hat. And if we move the negative sign within, we resolved. We can say that, okay, this is also actually equal to the definition of moment inertia. So the middle term is a definition of moment inertia. So finally, what we do here is that we can just replace this term as omega 2 times j omega 2 because the middle term is the same as moment inertia based on the definition here. So finally, what we have here is that the active dynamics of rigid body can be expressed as the moment inertia times the angular acceleration expressed in the rotating frame, plus some Coriolis and centrifugal force terms by the omega 2 hat and j. And then this entire system is driven by the total sum external torque. So the active dynamics is as follows. So j times omega 2 dot plus omega 2 hat times j times omega 2 equals to tau. So for a quadrotor, if we can design a tau, if we control the tau, then we can control the omega 2 so that we can control the attitude of the system. So I will also go over some modeling of the propeller and motor model because the main actuation is from the propeller thrust. So for a propeller, it actually rotates to generate the thrust, right? It is powered by a motor, this brushless or brush motor. So on the shaft, we have a torque that makes the propeller spin. And while it spins, it generates a drag. So propeller will generate a drag. And when these two, the torque provided by the motor and the drag generated by the propeller balance each other, then we will have a steady state thrust as a function of the rotating speed. So for the propeller thrust model, usually we use the model from the UIUC database. So by defining something called advance ratio, which is the division between the forward velocity and the rotation speed and the disc diameter. And we use this advance ratio to do the lookup table. And we can get the torque, power, and the thrust. Thrust coefficient, power coefficient, and torque coefficient. And then we can, then we can get the thrust at a given rotation speed and the forward velocity. So for the motor modeling, you can simplify the brushless motor into a brush motor. Say and for a brush motor, the dynamics of its motor is in this format. So basically, the back EMF is a function of the rotating speed. So if the rotation speed is high, the back EMF is high. Okay. And the control input you put into this system is the voltage input. So if the rotation speed is very high, so it will actually reduce the effective voltage. And because of resistance, you will still have some current here. And so the torque available is a function of the current. So if the motor spins faster, the lower torque you will have. And since the torque decreases and the drag on the propeller increases, you will reach a balance at some rotating speed. So this is by using this chart from the UI user database, then you can do lookup table and get the steady state thrust and also torque on the propeller. Okay. So that is some high fidelity ways to model the thrust. And for quadrotors, you can simplify this process by assuming that the forward velocity is just 0. So because usually what we do is a quadrotor flies horizontally or just hover. So the forward velocity is very small comparing with the rotating speed. So if we say the J is approximately 0, then it means that the CT, CP, and the CQ are all constants because we can just use the first value from the chart, right? So it's a CP, CP, CQ, they are constant. And then we can say that because this is the T is a function of the square of the rotating speed, we can say that the thrust and also the torque generated by propeller for quadrotor case is a quadratic function of the rotating speed of propeller. So we can safely assume that for if we say we use some ESC, use some electrical speed controller, we can assume that we can control the omega of the propeller spinning speed. Then we say the thrust generated by the propeller is just a quadratic function of the rotating speed of propeller times the constant. And also it's true for the moment because the torque coefficient of the propeller is also a quadratic function. If the torque of the on the propeller is a quadratic function of the rotating speed if the CQ is a constant. So in this case, we can do some further analysis, say that, okay, since these two are both the quadratic functions of the rotating speed, then we can say that, okay, so if we want to generate a certain amount of lift, then the propeller will create a certain amount of torque on the disk. And the relationship between them is a linear relationship. It's actually a scalar kappa times the magnitude of the lift. So now this gives us a simplified way to obtain the forces on four rotating propellers if we want to have a desired force and torque on the entire body. So for control controller purpose, we always want to have the for propeller to generate a desired torque and lift on the quadrotor. But in the end, we are going to control the rotating speed of every individual rotors. So the thing is that by using this relationship, the linear relationship between the torque and the lift, we can do something called a thrust mixing. It means that if we want to set the total lift, it's like a collective lift or the total lift, and the total moment on the quadrotor, by using this relationship, if we can get kappa from the CQ, the ratio between CQ and CT, and also the L is the arm length, L. Then by solving this linear equation, we can get the lift on individual rotors. And then finally, if we assume that the lift is a quadratic function of the angular velocity, then we can get the rotating speed command for each rotors. Then we can put these commands into our electrical controlling system and just let the EST to do the work to control the drones. Okay, let's thrust mixing. So by inverting this matrix, we can get the Fi, and by using the Kf, we can solve for omega on each propeller. So to sum up, the quadrotor is assumed to be a rigid body. So based on our analysis of rigid body modeling, the total, the mass times the moment of the inertial acceleration equals to the total force on the system. But the total force is actually consists of several different parts. So the first one is actually the lift. So F1 is a summation of several different parts. So the first one you can see here is that this is the magnitude of the lift. But for a quadrotor, the lift can only be perpendicular to the disk, right? So it's always pointing to the z direction. So here, E3 is the unit vector in z direction, and then we apply a rotation matrix to get the lift in the inertial frame. The second one is easy, right? So gravity pointing downwards in the inertial frame. And the third one is some kind of F bar, which is composed of all the drag and the external gusts you can have if you want to do further modeling about the system. So tau is just a tau generated by all the propellers, and plus some additional disturbance term caused by the drag, the wind, the drag, and the model uncertainties. So the thing is, in the second part of the lecture, I'm going to tell you some different ways of applying automatic control on such systems, such that we can control the x and the v to follow a given trajectory. Okay, so I will cover several topics about the PID control and LQR, and also I will give you some brief introduction about nonlinear control in the implementation part. Okay, so PID is the most commonly used one. So simple example is here. So if we have a double integrated system, x double dot equals u, and by defining a position error, E, as a difference between your desired position, such as trajectory, and the current position, we want to compute u such that this E goes to 0 as time goes to infinity. So in this case, what we want to do is we want to design the dynamics of E such that it resembles a second order stable system. So here we have if we can design controller such that E double dot plus kV times E dot plus kp times E is equal to 0, it means that the E dot will converge to it because it's stable and the input is 0. So if it's a stable system and if the input is 0, and then it will eventually converge to 0. And then if we apply the dynamics and also the error definition of this system into this formula, we get the following. So we replace double dot as x double dot desired minus x double dot t. Then, because x double dot t is also the control input, so we can replace the x double dot t as a control input and move it to the right-hand side of the equation to get the control input as a feed-forward term. This one is a feed-forward. Feed-forward term plus a D term and a P term is the derivative term and the proportional term. So this is a very typical control called PD control. Right? So you have a derivative term to damp out the excessive velocity, and you have a P term which drives your equation state to the desired state. Then what about PID? So the purpose of adding the integral term is that sometimes, quite often, we have persistent disturbances, such as wind or some parameter uncertainties that are persistent. So in this case, the PT term is not enough for achieving zero steady state error. And in this case, we need to integrate the error with respect to time to add additional compensation for the persistent disturbances. However, if you set too high of this Ki term, integral term, it will add instability to your system, such as the wind up. It's like a saturation in your control input. So there are some 3 figures of how the response of the system when you pick different Kp and Kv. So for stabilized system, we need the Kp and Kv in this expression. So in this formula, to be both and also xd times x. So the E is defined by xd minus x. So in this case, we need both Kv and Kp to be positive to achieve a stable system. So somehow, sometimes when you read other papers, there are different definition of error. Some people use x minus xd rather than xd minus x. So in this case, then you need the negative gains to stabilize, right? Because the E is like negative. And if there's no damping term, you'll get a marginal stability. So because you just keep oscillating around the desired path. If the Kp and Kv are both negative, it becomes unstable. Then the key idea is how to design Kp and Kv such that we have with the system will reach a desired performance. So before that, we can there is something called alternative parameterization. So basically, in terms of achieving performance, for a simple system such as double integrator, we can replace Kv by 2 times theta times omega n, and Kp with omega n squared. So theta is the damping ratio, and omega n is natural frequency. So typically, we want to pick theta as 0.7 to 1, and the frequency is around TR, which is your rise time divided by 1.8. And if you want to settle in time, if you set a settling time, then you need to then the theta and the omega n should also satisfy this relationship. So basically, if we want to achieve a desired performance, such as settling time and rise time, then you need to calculate omega n and theta, and use these 2 variables to form Kv and Kp. Good? Okay. So that's the definition of a rise time, some rise time, settling time, and the peak time. So this is the rise time from 0.1 to 0.9. And settling time is that the trajectory afterwards is within 1% of the error band. And also here are some different response if you pick different theta and omega. So in terms of achieving desired performance for a simplified system using PID, you can just use theta and omega to determine the feedback gain of Kp and Kv. Good. So in addition to that, so if you are going to apply this on slightly complicated system and you do not want to calculate theta and omega, here, so I will also provide you a way to by trial and error, to manually adjust again, so that you can tune the PID to achieve better performance. So before that, we take a look at this very simple double integrated system. So 1 over S is the integrator. So we integrate twice to convert the U into the acceleration. And in the middle, we have the V, or the X dot. So this is X, this is X dot, and this one is U. Okay. So by applying the PD controller, we need the error of the system. So we set the error as the goal, the x minus xd. So right now the error is now is a little bit different from the previous, but it means that we need to pick a k we have to be negative values, right? So E is x minus xd, and this is E, and this is E dot. So here we pick for this system we can pick kp and kd to be 4 to have this response curve. But you can also try other different values. But as long as they are both around relative reasonable values should be okay. And here, because I picked the E to be a negative definition from previous slides, you need to add a negative 1 here to convert the positive gain to negative gain. So if we have too large of Kp, it means that you have a higher overshoot. So now I increase the Kp by the ratio of 10, but keep the Kv or Kd the same. So previously we have 4 and 4, now it's 40 and 4. Then you will see, okay, the system responds much faster, but the overshoot is very high. So if you say, if you see that if you apply your PID to a system and you discover that okay, the overshoot is very high, then you have two choices: either to reduce the proportional gain, or you increase the derivative gain. And if we do the opposite, so if we keep the Kp the same, but increase the Kd or the Kv by a ratio of 10, you will see we have a very, very long settling time. So the system responds very slowly. So if you find your system responds too slow, you should reduce the Kd or increase your Kp gain. Okay. Now, what about the integral gain? So in addition to the U here, we have some external disturbance. It's like UE. So the total equations of motion is U plus UE equals to double dot. And UE here is some kind of unknown force. So in the drone case, we can say we can model the gust or some parameter uncertainty as a UE, but this is unknown. But on the other hand, UE is persistent, right? So it always exists. So if we still use PD, we will have a steady state error. So this is our final steady state value, but 5 denoted by the dashed line is the goal. So you will have a steady state error. So in this case, what we do is that okay, since we have persistent external disturbance, we add the integral gain. And the integral gain is 0.3 to the system. So after the integral is added, you will see that okay, the steady state error goes to 0 and second goes to infinity. But the thing is that if you have too large of a Ki gain, so the integral gain, you will have a very large oscillation, very large overshoot, and also very long oscillations in the response. So integral gain is good for canceling steady state error, but you should be careful not to set too high values for that. Good. So rule of thumb. So how to tune? So if you are given a system that can be treated as black box, and then you are asked to develop a PID controller. The first thing you do is that you start with proportional gain, right? Just try proportional gain and see whether the result will go to your desired location. But even if it does not stabilize, it should be a very good start. For quadrotors, you can pick 1, 5, or 10. And then after that, you need to pick P again, so the derivative again to pick, such as the final value settles down as some steady state value. So even if there's a steady state error, it should be fine at this stage. And finally, after you tune the P and the D gains, such as the system does not have very high overshoot and settles down within a reasonable amount of time, then you can increase your integral gain. But usually the rule of thumb is at roughly 10% of the proportional gain. So you can use this value as a start for tuning the eigengain. Okay. So if the settling time is very long, then try to decrease your derivative gain. And if the oscillations is too strong, decrease the integral gain. But I would say that for complicated dynamics, this rule of thumb may not be effective. So we might rely on some more sophisticated control methodologies for designing controllers. But for simplified systems such as the position control for quadrotor, we can still use this rule to tune the gain of PID. Okay, PID is simple, right? And but for complicated systems, it may not work because of the dynamics and all the coupling between states. So one alternative solution is to use the so-called linear quadratic regulator. So it's stated as follows. If we linearize the system at some operating point to get the linearized model, for example, if we linearize the quadrotor at the hovering state, we should have a system comprised of x dot equals ax plus bu. Right? Now the u here is the delta lift and the delta torque on the quadrotor. Then we say, okay, so we want the system to settle down at some given at some time. And also what we want here is that because the controller has upper limit, we do not want to we do not want to saturate the controller. So we also want to penalize the controller input during the motion. So based on these two ideas, we'll construct an objective function as follows. So the objective function composed of two different terms. This term is the cost during the flight. So the Q matrix here denotes the error of the states. That's the performance. And R here denotes the weight of your control input. So it's like a control effort. And now the final term is called the terminal error. So we also have a penalty if you do not reach the terminal state. Okay. Then the problem here is that how do we design U such that this J is minimized? Okay. So by the way to do this is to apply Pontryagин's maximum principle. So I won't go through too much of detail, but here I listed the major steps. So the first step is here is that we construct something called a deterministic Hamiltonian. So it's a summation of your cost during the flight with a Lagrangian multiplier and your system state. So it's a constraint. So it's a very typical constraint optimization where you have an objective plus the Lagrangian multiplier times your dynamic constraint. So by applying Pontryagin maximum principle, we have the following three conditions at the optimal states. So if we say we have already found the optimal solution of x and u, it should satisfy the following. The first one is obtained by taking the derivative with respect to the Lagrangian multipliers. So this will just give us the constraint. So x dot equals to ax plus bu. It must be satisfied, right? Because it is our system dynamics. And the second one is the dynamics of the Lagrangian multiplier, which is obtained by taking the derivative with respect to x. And however, you will see that this Lagrange multipliers must be the same. So its terminal value is determined by the terminal value of x. So also, by doing the kind of derivative around the control input with respect to taking the derivative of the Hamiltonian with respect to the control input, we also need to set it to 0. And this will give us a control output based on the Lagrange multipliers. So by applying the Pontryagin maximum principle, we have these following 3 equations. So the first one tells us to solve the ODE from the beginning of time. Right? The second one tells us, okay, we know the final value. We want to solve backwards in time. So it forms some kind of boundary, 2-point boundary problem. This is very hard to solve actually in terms of numerical solvers. So alternatively, what we do here is that we guess a form of a solution. So we constrain the lambda t to be a linear map between to be the product of a p and the x. So if we use this assumption and we apply this assumption in the control input, we can simplify this optimality condition such that we can get an explicit result to solve for p and also u. So here now the lambda is given by p times x, and then what we do is that we apply this condition and to this equation such that we can have the following. So lambda dot, we can use the chain rule to calculate lambda dot, and then we apply both the controller and the assistant state to get this p dot x times p times all this in here. So the first term is the same, and the second term here is because we have p times x dot. So p times x dot equals p times ax plus bu, and also it equals to p times ax minus r inverse b transpose p. So then we can pull the x out from the parentheses and put it at the very the very end. Okay, so we have the final form in this format. Is by rearranging terms. We should have oh no, it's not. Since lambda dot also equals to the second equation, so this is terrible. Equals minus p dot plus p times all sum together times x. So this first term is obtained by using the system constraint. The second term is obtained by using the dynamics of the Lagrange multipliers, and then we can equate them together to obtain a function that is only obtain an equation that is only relative to x. So in this case, we can eliminate the Lagrange multiplier lambda. In this case, if we say it is satisfied for any x, then we basically say, okay, we pick x. We can pick x such as at some very special value, such as 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. So then this equation boils down to this algebraic, this Riccati ODE. So basically here we have a P, which is a derivative of this matrix with respect to time. It equals to itself times the system matrices as well as the weighting matrices. Note that this P has a terminal value of P1. So in order to get a P for every time step, we need to integrate backwards from T. For rigorous speaking, the LQR gives you a time varying feedback because the P is a time varying value. The thing is, for engineering practice, we can assume that the T is, so we only care about the steady. If we reach a steady state, it's okay. So we do not care about the, like a 100 second or 1,000 second ago, it will go anywhere. So here, if we say, if the T, where the T settle down is very long, the equivalent to say that T is approximately infinity. Then we will say that, okay, if T is infinity and it settles down, because we calculate, because we should integrate it backwards. So at the time that is very close to the initial condition, the P should settle down. So in this case, we can assume that at the initial, so something near the initial case, something near the initial state, the P dot is approximately 0. So the P settles down to a constant value, terminal value. So then, if we assume that the P dot turns 0, we can simplify the Riccati ODE to a algebraic Riccati equation. And then now the only problem is how to solve for this equation, this Riccati equation to get P. So if we have P, and we replace the PT here with the constant value P, we get the LQR feedback. So now the problem is how to find such a positive semi-definite P that satisfies this equation. So the condition is that if the linearized system is something called stabilizable, so then it is guaranteed that there is a solution for P to be semi-positive definite, and also in the meantime satisfy the Riccati equation. So what do we mean? So now the thing, what do we mean by being stabilizable? Is that if you have a system x dot equals a, x times bu, if the part that is unstable, that is uncontrollable, is inherently stable, then we call it is stabilizable. So it's different from controllable. So for controllable, we said that we can control the full states, but that is not quite. That is often not quite realistic for some special systems. But if the uncontrollable part is stable, then if we can design controller to control the stabilized part, then the entire system can all still be stabilized. So this means that for a linear system, if we can find a T, a transformation matrix T, such that if we have another state which is a transformed state of T, and for the transformed state, we can separate. So for the transformed state, the A matrix has a very special form, and also B matrix has a very special form. So if we can find the T, the transformation is such that if we transform the original state to form a new control system, such that the state matrix A has this upper triangle form, and also for the control matrix, all the entries corresponding to x2, the lower part of the x is 0. So if we have this alternative form, and if A22, so the matrix at the bottom right corner is Hurwitz, means that it is stable. So if this one is stable, it's a stable matrix, then the system is called stabilizable. So basically, what do we do is that we make a transformation and separate the states to a part that is controllable, meaning the upper part, and the part that is uncontrollable, meaning the lower part. And if the lower part is inherently stable, then the entire system is called stabilizable. So if it's stabilizable, it is guaranteed that we can find a P that satisfies the algebraic equality equation. So you can find the P to get the control input. Okay, so for MATLAB implementation, you can just use LQR command in MATLAB, right, without calculating, doing the manual code. Now the thing is that okay, so we kind of circumvent the tuning of KP KTKI games in PID, but right now we have we have some other issues of picking Q and R, right? So we also need to pick something in order to let this thing work. But then how to pick Q and R such that the system has a desirable performance? So the rule of thumb is this: the Q and R controls the performance and the actuation, the amount of actuation you can put in the system. So if you pick a large Q, it means that if you penalize the state error, you put more emphasis on the state error, then your performance will be better. If you instead you set the R to be large, then what do we say as okay, so you penalize more on the control input. Then your response will be slow and you will see some oscillations. Then so for matrices Q and R, what I mean by picking large or small usually means the eigenvalues. So here Q must be a positive semi-definite and R must be positive definite. Because in the algebraic equality equation, we need the inverse of R, so it should be always invertible. So the common practice is to just pick Q and R, be a diagonal matrix. Then by adjusting the values on the diagonal, you control the eigenvalues. Okay. For example, Q equals say Q1, Q2, Q3, and R equals R1, R2, and R3 for like three-dimensional system. So if you set a larger Q1, Q2, Q3, you'll get a higher performance. You set a larger R1, R2, and R3, you penalize more on control input, so your response will be slower. Okay. But one important thing is that if you scale up both Q and R by a same scalar, the performance will be the same, right? Because what you do here is only to add a scalar on the total objective function, but without varying where the objective function is minimized. So increase both Q and R by a same factor will not change performance. So I'm not going to go through all the detailed performance about nonlinear control because it's way beyond the scope of this lecture. But I will tell you some key aspects of how to do the nonlinear control. So previously, all the PID, the LQR are all applied to linearized systems. So, but if you want to do large and agile maneuvers, you have to deal with nonlinearity in the system. Right? For example, the attitude motion is nonlinear. Right? So if it's very close to the equilibrium, you can say, okay, it's linear. But if you do large maneuvers, it's very nonlinear. So if you want to achieve a better performance, you need to rely on some nonlinear control. The first and the most widely used method is called the Lyapunov-Dirac method. So here I provide you a link to a very to a key paper so that you can take a look for the how to apply Lyapunov-Dirac method to a quadrotor. So the process is to guess a Lyapunov function and then guess a controller and then prove that the Lyapunov function, the derivative of Lyapunov function is a negative definite with respect to time. So the second major part is the learning-based control. So nowadays by using something called machine learning or reinforcement learning, we can formulate a neural network. Right? So neural network can approximate a very abstract nonlinear controller, and by putting some penalized functions or some reference data sets, you can train the neural network to fly the drone according to a given trajectory at a given performance. So there are also a plethora of references that are available. So I provide a link to a very typical paper here. The third one is MPC. It's called a model predicted control. It's a generalization of the LQR, but on nonlinear systems. So for LQR, we can calculate the Riccati equation explicitly because everything is linear, right? But for nonlinear system, you have to deal with Jacobians at each different state, and you need to calculate U, which is dependent on the state and time. So that's called MPC. You predict your system on a horizon that is several seconds ahead. Then you calculate the U. So the U here is obtained purely numerical. So this is also widely used in robotics and quadrotor controls. So a very typical paper is provided in reference 3. So if you have interest, you can read it after the lecture. Okay, the final part is that then how do we control the quadrotor based on all the control methodologies we have already learned? Now the key idea here is that for a control on the quadrotor, we follow a common paradigm called the nested control architecture. The reason is that for a quadrotor, it is an under-actuated system. It's not fully actuated. So we have to control the attitude in order to control the motion in the translational channel. Right? So usually the lowest level of control is how to stabilize the attitude such that we can point the lift direction to anywhere we want. And then on top of that, we build the trajectory tracking controller to generate a desired lift for the attitude controller. And on top of this, there may be some other higher level missions such as manipulations or swarming or manipulations, trajectory tracking, or coordinated fly. So all the controllers in this lecture are built upon this nested structure of trajectory, attitude paradigm. So here is a more concrete example. So for a quadrotor, the most inner is the motor control, so where we use ESC to control the spinning speed of motor by using the rotor mixing formulas I introduced in the previous slides. And on top of that, we have rate control, so control the body rate by varying the torque on the propellers. And by controlling the rate, we can control the angle to point the thrust to different directions to control the position of the quadrotor. And on top of that, we have some high-level tasks, such as formation flight or area manipulations. Good. So then how do we implement a position stabilization control on a quadrotor? And the first thing we do is that we define a error, right? So the error in terms of position and velocity by using the desired state minus the current state, and also the desired velocity minus the current velocity. And we want to design a system such that, similar to PID, those tracking errors goes to 0 as time goes to infinity. Now, the first example here is that I use something called a small angle assumption. So this is a controller, especially for controller quadrotor to fly at a relatively low speed and with a lower maneuverability. So quite often it's just to stabilize a quadrotor at a given position. So then in this case, it is reasonable for you to use the small angle assumption. So basically, what we say here is that all the angles are very small, such as phi is equal to 0, is approximately 0, theta is approximately 0, and psi is approximately 0. So by using this assumption, we can conclude that the Euler rates, the rate of change of the Euler angles, is approximately equal to the angular velocity measured in the body fixed frame. So we can replace this nonlinear equation here. We can replace the nonlinear equation here with kind of a linearized attitude kinematics. And okay, so based on that assumption, we can build a control structure in Simulink, and here is a test case building in the Simulink. And also, this is good for slow movement, hover, such as hover and static cruise, but it is not good for aggressive movement, such as drone racing. So the controller consists two parts based on the cascade structure. So this part is a higher level part, so it generates a desired lift based on the position error of the coordinate of the quadrotor. And after that, if the desired lift is generated, say F tilde, then what we do is that in the attitude controller, we will convert this desired lift to the torque on the quadrotor to control the Euler angles, such that the actual lift will coincide with our desired lift. So in the translational channel, we build a PD controller. So this is X, this is a P. So this is a KP gain, this is a KV gain. So this is V. This is V equal to X dot. And of course, we should have a minus sign because I defined the error as X minus P. So in the translational channel, the desired lift is a result of a linear PD controller. So at this output, it is so the output of this calculation of a PD controller is actually a minus KP times E minus KV times V. So it is in the 3D space, the three-dimensional space. This saturation here is that we do not want the lift in the z-axis to be too large or too small, because if it is too small, if it is too large or too small, the propeller is not going to generate a negative lift or excessively large lift. So we need to saturate the control input here, such that our actuator can actually produce the amount of lift. So now this is so after so in addition to the PD control terms, we should have a gravitational compensation term. So the lift force is going to first cancel the gravity and then drive the quadrotor to the given location. So by summing up these two, we get the F tilde. So F tilde actually equals to minus Kp times E minus Kv times V plus Ag. Right, so the gravitational compensation force. And then in the attitude channel, because we have the desired lift, then we can extract the magnitude of the desired lift to be the total lift generated by propellers. And we can also extract N, the direction of the desired lift. So N is a unit vector. So this is the direction of the lift. So the direction of the lift actually corresponds to the desired Euler angles of the system. So then by using the arctangent tool, this is your desired direction. And by using arctangent tool, we can calculate the desired phi angle, and as well as the desired roll angle, roll and pitch. So this is the control diagram inside the attitude control. Over here is the F tilde, and after so this part, in this part, we can extract the magnitude of F tilde. And since the F tilde, the magnitude of this F tilde is obtained, so here we can extract the direction of F tilde as n tilde. So if we have n tilde, these two octant functions will give us the phi d and the theta d, which is the command attitude, command pitch, command roll and command pitch. And here for the yaw angle, we can set a yaw angle as a constant. So this is phi d by ourselves. And since we have, so this is the attitude channel, and here is the rate channel. So the attitude channel, so all the Euler angles omega d, if you have Euler angles d, and then we can obtain the actual Euler angles from the simulation. And then here is the delta of Euler angle. So it's a difference of the Euler angles between the desired value and actual value. And here we can also, so this is a high pass filter to do a filtered differentiation of the desired Euler angle. And this is the actual body rate. So at this port, you will get omega dot. You get minus omega d dot. So which is delta omega d dot. So this is a speed feedback. This is a position. So here is a position feedback. I would say position is at the desired attitude. This is your desired rate, the error of the rate feedback. Then what we do is that we also use a KP, but right now is the KP and KT is applied in the attitude channel. So we have a cascade structure, right? So we have a previously we have a translation channel and then produce a desired lift. And we use desired lift to construct a desired Euler angles, and then we convert desired Euler angles to a final desired torque on the system by using the PD controller. The final simulation is showing in this figure. So it goes to the 5, 1, and 0. So now for a more complicated problem, such as the one here, so if we manage to do the controller by using the small angle assumption, instead of just let the drone hover at a given point, we can use its controller to control the drone to fly along a given path at a given constant speed. So here, the path is determined by a starting point P and a direction vector Ni. And what we want to do is that we want the drone to approach to this straight line, and then finally it will converge to a given cruise speed, such as v, right? So then how to describe the position error? Since we have a cascade structure, then the first thing we need to do is to get the position error and the velocity error. So then what is the position error in this case? The position error here is that if we take the position error from the starting point of this trajectory, then the distance or the value or the position error from the trajectory is actually this vector minus its projection onto the path. So if we say this is A1 and this projection is A2, so this vector from the starting point of the trajectory to the center of mass of the quadrotor is A1, and its projection onto this trajectory is A2, then the E is actually A1 minus A2. Right? So it only takes into account the vertical displacement, perpendicular displacement of the drone away from the desired path. Then how to calculate this? So A1 equals to x minus P1, Pi. So this vector is x minus Pi. And the projection of this A1 onto the path is A1, the inner product between A1 and N times N. So this is A2. So E equals A1 minus A2 is equal to x Pi minus it's like A1 minus N transpose A. So it equals to, so if we extract A1, it equals to identity matrix minus N times N transpose and A1. So which we have, this is exactly what we have here for the position error. It's called a path deviation error. And the path velocity error is just your current velocity minus your desired velocity. And also, it's very important that these two, the desired velocity is perpendicular to the path error, because we only want the velocity to converge to we want to converge to the same direction as Ni. So it has no component in terms of direction of the path deviation error. So, okay, that's a figure to explain the path deviation error. So how to get this? So this one is the projection of the position error from the starting point of this path, and this is path deviation error, which is EXI. So finally, what we'll do is that we're going to use the path deviation error and as well as the velocity error to construct our cascade controller. So here is a Simulink model. The difference between the path following controller and the position stability controller is that now we need to take into account the identity matrix minus N times N transpose. So from here we get x minus P. And by doing this matrix multiplication, we get the projection of xp onto the, we get the path deviation error. So this is actually xi equals to n minus n times n transpose times x minus p. And because this is a position error in general, we can use a Kp again. And and this part is the velocity error defined by just subtract the VQ and VDI, and this can be treated as a derivative feedback. So we term this feedback as a KV, and then we sum together to form a PD controller. So using the same ideology, but right now the position error is different because we have this path following problem. And finally, we need to saturate the force in the z direction because of the actuation capability. And we need to add the gravitational compensation force G to produce the final F. So now the final F is equal to Kp times EXI minus Kv times EVI plus G. So, well, in this case, the attitude controller is the same. So for the attitude controller, it's a kind of modular as a design, right? So we only change the definition of the positional controller, but as a controller, we can just reuse the previous ones. So here's a simulation. You can see that from the start position, it converges to the desired reference path. And also, for the velocity of the quadrotor converges towards the desired velocity. Okay, the final part is it's about cascade nonlinear control. So previously, for the previous controller for position stabilization or the path following control, we use small angle assumption. So that is very constrained if we want to do high speed maneuver or agile maneuvers. Then how do we produce a controller that has no such limitations? So here is a way to construct such controllers. So I use this method from reference 1, which is called the differential flatness of a controller of a quarter dynamic subject to a rotor drag for accurate tracking of high-speed trajectories from Dr. Scaramuzza's lab. So as I said in previous slides, so one way to circumvent the problems over Euler angles is to use rotation matrix. Right? So this time, instead of forming a desired Euler angle based on the path error, we're going to form a desired rotation matrix based on the position error. So this is the system setup. We have a word frame defined by X, W, Y, W, and Z, W. The body fixed frame is XB, YB, and ZB. So in this case, in this paper, he used ENU frame. So the Z vector is pointing upwards. The body fixed frame is denoted as B. The word frame, which is also the inertial frame, is denoted as W. Okay. Now we want to design a U such that the controller, the quadrotor will fly along this given path. So for a trajectory tracking problem, often we need to say that our goal is to set the desired accelerations of the quadrotor based on its current state and the path error. So if we can set the x double dot, which is A, to a value that we want, then we can control the drone to perform a trajectory tracking for any curved trajectory rather than just a straight line. Okay. So here is the dynamics of the quadrotor used in the paper, but it's also, yes.
In the previous slide, I had a question.
Yes.
Are those X and Y kind of switched at once?
X, Y, oh, yeah, sorry. This is XW. Thanks. So the typo here. So the dynamics of a quadrotor is expressed in this format. So it's the same as what I introduced in previous slides in the rigid body dynamics section. But the difference here is that this paper also considers drag and also some kind of cross-damping terms on the attitude channel. But so for this drag, this V is the the flying velocity. The R here is a rotation matrix between W and B, the W frame and B frame. Okay, and now you can see that this kinematics has this relationship between the omega and the R. The D is a drag coefficient, so D is a diagonal matrix. So you can just treat this as a drag coefficient. So basically, what it does is that okay, we convert the inertial velocity into the body fixed frame, and then we apply the drag coefficient. What's the time right now? And it's the same for the attitude channel. So there is a cos fitting terms between the V and the omega. So we have some external disturbances based on the velocity. And the thrust model is very simple. So this C is just our F, it's our collective thrust. It's the total thrust generated by propellers. It's a quadratic function. It's a command thrust, which is the thrust actually. So the thrust is received from the controller, and plus some kind of a disturbance term in the thrust model. So they also consider there's a parameter uncertainty in the thrust model. So then how to design a controller for this nonlinear system without using Euler angles? The first step here is that because we want to set the desired acceleration based on the trajectory. However, the desired acceleration is a 3x1 vector, so it has only 3 inputs. But we have 4 control inputs for the system, meaning that we need to specify one additional requirement for our control. So here, what we do is that we set the yaw angle per psi as a given yaw angle. So we provide a yaw angle as a per psi. And then what we do is that we construct an auxiliary control coordinate system. So XC. So it's called a frame C. So the frame C is just a frame. It's a frame omega. No, so it's a frame W rotated by the per psi angle. So it's like a rotated version of the water frame. Okay, so this is an XC. And since XC is determined by the heading angle per psi, we just assume that we constrain the x-axis of the body fixed frame to be at a position where is a projection onto this xw yw plane to so the projection of xb onto the xw yw plane is the same as xc. So you can imagine that the xb vector, so the x-axis of the body fixed frame is xc, but it rotates around the yc. So it's like a pitch up a little bit. But how much, right? So what is this angle? Now this is a trick. So how to obtain this angle, or just how to obtain the xb? So in the paper, what he did is that by looking at this translational motion equation, also by using the definition of D, one can move the V to the same side of the equation V dot. So now the A is V dot. It means that your desired acceleration. So for example, you can set your A dot according to your distance from your trajectory to the actual from the position to your actual trajectory. So here we just treat A as a 3x1 vector that can be set by a user. So by moving this one to the left-hand side, right-hand side of the equation, we have this formula. So basically, it's the same translational motion. But if we times the vector of xb, so if we define alpha as in this format, so basically it says if we times xb on both sides of the equation, and because xb zb is 0, xb transpose zb is 0 because these two axes are perpendicular, xb transpose yb is also 0. If we do the this multiplication, then these two terms are cancelled. And also this term is also cancelled. So the resulting equation is that xb transpose times alpha, which alpha is the remaining three terms here. So it says, it tells you that right now, even though we do not know the direction of the body fixed frame, we know that the xb, the x-axis, is perpendicular to alpha, which is determined by your desired acceleration, the gravity, and also the drag. So previously, we said that the xb is from xc, but it rotates around the yc axis. So xb should also be perpendicular to yc. And now, from this equation, we say that, okay, xb is also perpendicular to alpha. Then in this case, we can just say, okay, since we have two perpendicular components, then how about we just do a cross product to get the actual direction of xb? Right? So this is a yc, and this is alpha. This is a plane formed by alpha and yc vector. So this vector, so the xb should be perpendicular to this plane. And then the way we obtain is that we just use the yc cross product alpha to obtain the xb. And similarly, we can. So previously we term xb transpose on both sides. Now we can term yb transpose on both sides of the equation. So by doing the same procedure, we obtain something called beta. So we can also say, okay, this beta is perpendicular to yb. But we also know that for the body fixed frame, xb should be perpendicular to yb as well. But we just obtain xb, right? So we can obtain yb by performing the cross product between beta and xb. So here is a diagram. This is xb, this is beta. And this is a plane forming by the xb and beta. So the yb of the body fixed frame should be perpendicular to this red plane. Now we get a second column vector, second basis vector of the rotation matrix. And the third one is that, okay, so zb must be perpendicular to both xb and yb, so we just do the cross product, and we should get the result. Right? So here's yb, here's xb, and this is zb. So recall that for a rotation matrix, if we find the basis vector expressed in the inertial frame, we can just construct the rotation matrix by using by just the row stack or the basis vector. So this is our RD, our target attitude of the quadrotor. And also, if we do this zb transpose times both sides, we can get the desired lift on the quadrotor. So this C is a collective thrust. So we can obtain this by so basically it just tells us that this is a force, and this is a force component on zb. So this is zb. This is a force. So it's like alpha times gzw times some drag terms. And this C is a projection of the F onto the ZB to get the collective thrust. So now the thrust is determined, the attitude is determined. Then we can pass it to lower level attitude controller to do the attitude control as well as adjusting the thrust. So in this case, we can see that there's no Euler angles except the theta, except the psi you set by yourself, right? But for alpha, but for the pitch and roll, we do not use pitch and roll here. We just use a rotation matrix. And to sum up, all the entire procedure is that, okay, so we need to manually pick a psi to get xc and yc, the coordinate. And by producing the, and by moving the v dot to the same side of the translational dynamics, we get this formula. And then we replace the v dot as some kind of a desired acceleration. So by multiplying xb transport on both sides of this equation, we get the alpha and the beta, which determines the direction of xb and yb in this three formulas. And then if you get your xb, yb, and zb, you construct R. And finally, you use the xb, use zb transport times the total acceleration, total force, to get your collective thrust. So once you have R and your C command, there is a lower level controller that can handle this. And this one, and also this is the controller you are going to use in your next project. Okay. Any questions? Yes. Yes, next lab, you're going to develop a controller, right? Yes. Yes. So any question regarding this process? So basically, what you do is you need to figure out these two terms, the alpha and the beta. And say if you have a trajectory, and if you're away from trajectory, then you need to design your ACC, basically the A here. Based on the error, you need to design an A. So this is your job to design the A. And if you get A, put in this alpha and beta, you should get R and C. And all lower level controllers are designed for you, are already constructed for you, so you can just use that. Okay, so there's some simulation from the paper. You can see this, it can track not only just a straight line, it can track a circle and some very complicated shape of the trajectory. Okay, yes? It's the damping ratio. No, sorry, it's the drag ratio. So so because in this paper, they also explicitly model the drag. So if you do not consider the drag, you can just set the dy dx to be 0 if you do not consider the drag.